So let's talk about some properties of waves. I've talked about the electromagnetic spectrum and wavelength of light, etc. But part of the reason we're talking about this, we're going to get into it soon, is that electrons have both particle-like and wave-like behavior. So we need to understand how both particles behave, but also understand how waves behave so we can truly describe the electrons and what's going on in the molecules themselves. So with waves, first we want to talk about interference. Interference, you guys have probably learned about physics or before, but what happens in interference, we can have constructive or destructive interference. For constructive interference, as shown here, this is when we have two waves that have the exact same pattern. So they have the same wavelength, the same amplitude, same frequency, same everything. Everything's the exact same. And they add together in a constructive pattern. When they add together, we see that the wavelength itself and the frequency stays the same, but the amplitude is actually increased. So it's a summation of the two individual waves, and overall the amplitude becomes higher. We can also have destructive interference, where when the waves are added together, they're what we call nulled out. They kind of cancel each other out in the process. So waves can go through both of these processes, being constructive or being destructive, and therefore canceling each other out. We also have diffraction and two-slit interference. Diffraction is when we have a series of waves going through some type of slit. As they enter into the slit, so the waves are going through and they hit the slit, and they start forming this more of a curved wave-like pattern. It's a diffraction pattern. The size of this slit here can be changed. So the size of this slit here can be adjusted. And we see if we adjust it to a really small, they become more curved in the diffraction pattern. So the size of that slit determines how those waves behave. Do I have a big slit so that I have a little bit of distortion to the wave, or do I have a small slit so I have a large distortion to the wave? From there, we could also have two-slit interference. Two-slit interference is where we have literally two slits, slit 1 and slit 2. So we've got some kind of light source and our waves leaving this light source. The waves are leaving the light source and eventually they're going to hit the slits. When they hit these slits, they're going to pass through the slit and they're going to reform whatever shape of wave they need based on the size of that slit. But they can start interfering with each other. We can start having an overlap of these waves coming off of these slits. And I realize these are not drawn well, and I apologize for that. My drawing skills were not contingent upon this job, and drawing on an iPad is not the easiest thing for me. But what we see is eventually these waves will start to overlap. And where they overlap is where we get this pattern. So we see the top view versus the front view. We've got black, gray, white, black, gray, white, black, gray, white. We've got these different areas in here of where it's actually hitting. And again, we can have constructive or deconstructive in this pattern. That's what we see here. Constructive versus deconstructive waves hitting, making our full diffraction pattern. So sometimes the waves react constructively, increasing what we have. Sometimes they're going to react destructively, nulling out entirely what we have, giving us the dark spots. The dark spots on here. So the dark spot is where they're nulled out. The light spots are where they're constructively adding together. So waves do this naturally. And electrons, again, can behave as both particles and waves. We also have refraction and trajectory of particles that we need to talk about. So we talked about, this wave diffraction. These waves are coming through from some type of wave source. They go through a slit, and we've got your diffracted wave. A wave does this. A wave comes through, and the crest will change shape and form this diffracted wave. If I had an individual particle, though, a particle would come in, and some particles would hit the barrier, and they would just be stopped. And some particles will travel through the barrier and not be stopped at all. Electrons behave as both, though. So what's happening here? How do we kind of correlate or bring these two concepts together? We know the electrons aren't being completely stopped, but they don't always behave as waves either. And so we've also got this refractive index when we talk about the particle behavior or trajectory of a particle. So pretend here we've got some kind of change in medium. Got a particle coming in here, it hits, and its trajectory is changed in the way the angle it goes in. This is due to whatever medium it's now traveling through. It's got an angle of refraction here. This is called wave behavior. Particle behavior, if I had a pure particle here, the particle would most likely just come in and just kind of fall down wherever it wants to. But again, the electrons are going to behave as both. This diagram here, perfect example of diffraction. We've got white light going in. We talked about this as a continuous spectrum. Got white light source going in. It's being diffracted through a slit, and we see that it separates them out based on the colors of the rainbow. So our pattern coming out, here is our pattern coming out, definitely looks different than the pattern going in. And that's because of this refraction that refraction and diffraction these waves undergo. So this brings us to Newton and Einstein. And Newton, 17th century, he worked on chemical physics, and he had an extremely accurate description for large objects or objects traveling well below the speed of light. 20th century, Einstein comes along and he develops quantum mechanics or relativistic mechanics, which we now know as modern physics. They're both correct is the biggest thing. They both were trying to describe how these particles were behaving. Einstein proposed that a beam of light behaves as if it were composed of a string of small particles or packets of energy that we call photons. H nu represents a photon because H nu is the energy of one photon. H being Planck's constant, nu being frequency. The energy of that photon depends only on frequency, not on your amplitude, intensity, or brightness. Amplitude is related to intensity and brightness. It makes no difference on that. It's just dependent upon the frequency. And remember, frequency is the number of cycles per second. How many cycles do I hit per second? The intensity of the light does correspond to the number of photons coming through. So the energy itself, the photon itself, is only dependent upon the frequency, but how bright that is depends on the number of photons we have. More photons, the more bright that light will be. A very rough analogy to all of this is that if you have a set of ping pong balls and you start throwing them at a window, one ping pong ball is not going to break the glass, but a baseball will. So this brings us about this particle nature of light, though. How do we go about understanding this particle nature of light? The main conclusions to everything that both Newton and Einstein developed was that in addition to behaving as waves, which is what they originally found, light also behaves as particles. And so Einstein was able to determine that energy is actually quantized, meaning that it exists in discrete amounts. Discrete means specific, like a specific level. So here is a really nice picture from your book that I like that shows quantized versus continuous. Continuous would be, you've got a ramp here, this ball's going to start falling, and it can anywhere on here. Quantized, though, is like a set of stairs. It has a specific allowable energy level that it will go to. So the ball's either going to be at the top step or the second step. Second step, third step, fourth step, fifth step, sixth step. It's a discrete amount of energy. It's your ramp versus your stairs. So again, the main point of all of this, energy is quantized. Quantum mechanics says that the amount of energy that can be transferred is quantized. Quantum mechanics, you hear about this term also in physics. If you haven't taken it yet, you will. But a lot of this stuff, Einstein, Newton, they're physicists. They figured this stuff out. But what all of this is telling me again is that I can measure the exact amount of energy that's involved. I can calculate the exact amount of energy. It also means, though, that the amount of energy that's transferred, either absorbed or emitted, is in specific units of size. These specific units of size is h nu, a photon. The smallest packet of energy is called a quantum, and an individual packet or particle of this electromagnetic radiation is called a photon. So we say one photon, the energy of one photon is equal to h nu. This relates back to what we saw in the previous section as well. So this wave-like property, again, light. We've always treated light as a wave. We can determine the wavelength of light. From the wavelength, we can determine energy. We know the energy is proportional to the inverse of the wavelength. So the longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. These are all things that we see electromagnetic spectrum, but we can also measure all of this. But, so up until this point, science was indicating that light, which we knew was wavelength, also had particle-like characteristics. So we know that light, we can actually determine the energy of that light source. Energy, that light can be absorbed or emitted in the form of energy, in the form of a photon. One photon we represent as h nu, h being Planck's constant, nu being your frequency, because energy is proportional to your frequency. So de Broglie comes along and proposes that, well, we know that energy can actually behave particle-like, then perhaps matter's always been treated as individual particles, perhaps matter can actually behave wave-like. And so we know that the energy of one photon is equal to h nu. That's Planck's law. H being Planck's constant, 6.626 times 10 to the minus 34 joule seconds. And we know frequency, seconds to the minus 1. So when you multiply these together, it gives you energy in joules. We also know Einstein's relativistic equation, the energy is equal to your mass times your speed of light squared. So these are both energy. We're going to set them equal to each other. And that's what we get here. h nu equals mc squared. But we also know that nu is equal to speed of light over wavelength. Because remember, energy is proportional to the inverse of wavelength. Well, your frequency is also proportional to the inverse of your wavelength, because energy and frequency are proportional to one another. So we can write this equation like this, or we can substitute in for our frequency and write hc over lambda equals mc squared. We're going to go ahead and solve for lambda. When we do that, when we rearrange this equation here for lambda, we find the equation to be hc equals hc divided by mc squared equals lambda. Simplify this, and we get lambda is equal to h over mc. Again, h being Planck's constant, m in this case is mass, specifically in kilograms, and your speed of light. Because Einstein's relativistic equation looks at mass. So that is m in mass, but we need it in SI units, so we use kilograms. This indicates that a photon with a wavelength lambda exhibits a mass, sometimes called the relativistic mass. What can I do with this information? Well, for a particle traveling at a velocity v, so be careful here where nu is frequency, V is velocity. And depending on the font you use on a computer, they often look the same. So you got to kind of use context here. But we were able to develop the de Broglie equation. Lambda equals h divided by mv, where the v here is, in fact, velocity. So m is mass in kilograms. V is velocity. How did I get to that equation? Well, we just figured out on the previous side that lambda equals h over mc, where h is the same, h is Planck's constant, m mass, but v here, velocity, we were using that as speed of light because we were looking at a photon of light. In this case, I'm looking at a different particle. This is for a particle, not a photon specifically, any particle traveling at a specific velocity. So we put in the velocity of that particle. It's not exactly the speed of light because it's not light that's traveling. We find from all of this that wavelength is inversely related to mass. And so basically the wavelength of a baseball, infinitesimally small, while the wavelength of an electron is just about the size of an atom. So we see classical trajectory, and I can't draw it well on the lines themselves. But in quantum mechanics, we're going to talk about this a bit more, a cool video we have coming in another video. This is the probability of finding an electron in this range. So the electron will travel this relative path, but it's going to be somewhere, most likely somewhere distributed in this space. But what can we do with this? Well, we can actually determine the wavelength that a particle is traveling using the de Broglie equation. So what is the characteristic wavelength associated with an electron moving at a velocity of 5.97 times 10 to the 6 meters per second? Well, let's see. We know lambda equals h over mv. We know h is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. M is mass. Now, you do not have to have the mass of an electron memorized. I will give you this mass, but the mass of an electron is 9.11 times 10 to the minus 31 kilograms. I don't know. I was thinking of Planck's constant. I apologize. Honestly, the only reason I remember this mass is I think of 911, like, you know, our emergency system. I think of Halloween. I don't know why, but those are what goes in my head. That's how I remember the mass here. You do not need to memorize that mass. And the velocity given here, 5.97 times 10 to the 6th meters per second. So let's go ahead and set up our equation. Lambda equals 6.626 times 10 to the minus 34 joule seconds divided by 9.11 times 10 to the minus 31 kilogram times 5.97 times 10 to the 6th meters per second. This gives me 1.21 times 10 to the minus 10th meters, which I can also simplify to 0.121 nanometers. Now first, let me show you how I got to meters from all of those units. In the top, I've got joules times seconds divided by kilogram times meter divided by second. I'm going to rewrite this because I know that 1 joule, I'm going to put this up here, 1 joule is equal to a kilogram meters squared per second squared. So I'm going to say kilogram meters squared seconds to the minus 2 times seconds, because this is all from joules, divided by kilogram meters seconds to the minus 1. The seconds here in the numerator cancel with one of the seconds here in the denominator, so this is now a minus 1. I've got seconds to the minus 1 divided by seconds to the minus 1, that cancels. I've got a meter squared divided by a meter. That cancels out one of my meters squared in the numerator and my meter in the denominator, and kilogram to kilogram, giving me an overall meter. Now, I do have 1.21 times 10 to the minus 10th meters here. A nanometer is 10 to the 9th. which gives me the 0.121 nanometers. Do you have to convert there? If the question asks, yes. If the question doesn't ask, no. I like to convert because I don't like scientific notation if I don't have to have it. That's why I converted that number. But we can use the de Broglie equation, so this equation, to calculate the wavelength of any particle. Any moving, traveling particle we can use, and we can calculate the wavelength associated with that particle traveling.